Hello everybody. We're going to start talking now about how we can calculate the forces that are acting on an object due to pressure. So for instance, if you have a tank and you want to know how much support you need to provide for certain fixtures and things like that, you can use these methods to calculate those hydrostatic forces. So these hydrostatic forces are due to the pressures of a fluid, and to totally understand them, we have to know three things. First, the magnitude of the force. Second, the direction of the force. And third, what we call the line of action, which is basically the point where the average force acts. And we can use that to calculate torque on an object. So we know how much force we need to add to make sure that the object's not going to rotate. Now, our choice of coordinates is very important here. So if we start with our coordinates from this point and go along this wall, or if we're looking at height, or if we're going up from the bottom, it's going to change our equations. These are the equations that we use to calculate what we call the resultant force, the force acting in the x direction and the force acting in the y direction. And then the two components together give us both the magnitude and the direction. So our choice of coordinates is very important. So we have to be very careful, make sure we use the correct coordinates, and try to change coordinates if we need to make the problem easier. There's also a quick note that I want to give you on pressure. If the pressure out here is atmospheric and the pressure above the liquid is atmospheric, we can recast this problem in terms of the gauge pressure. So the gauge pressure is going to be 0 at the surface, and it's going to be 0 outside. So that simplifies this, and we can cancel P0 from both sides. And we just have rho GH, and we can simplify our integral. And then the force is only the weight of the fluid, or the hydrostatic pressure. If we're looking at a sealed tank, and the pressure up here is greater than atmospheric, then P0 is going to be bigger than P atmosphere. So when we use gauge pressure, we have to account for that difference, and so we have some gauge pressure here. It's no longer equal to 0. And we have to add that into our equations. It makes the integrals a little bit more complicated, but they're still not too bad. We'll talk about them in just a few minutes. Now there are some tricks to this process. First of all, we can say that the horizontal force on a surface is the same as the horizontal force that's acting on a vertical wall. So if we take this surface, which is at an angle, and we have this imaginary vertical wall that has the same height as our real surface, the horizontal force acting on this vertical surface is the same as the horizontal force acting on this surface. So we don't have to worry so much about the angle. We just have to make sure we use the same height, and we can do perform the integral. We can also say that the vertical component of the force pushing down, is equal to the amount of weight that it's holding up, or the weight of this fluid that's on top of this surface. So that gives us a shortcut for calculating the horizontal and vertical components of the force and then getting its direction. We can also say that if this is air, and the fluid is here, and it has this level out here, so fluid, air, there's a horizontal force up, or a vertical force upward, that's equal to the weight of the fluid that's missing. So if the liquid is pushing up, then the total force is equal to the weight of the fluid that's not present here. So it gives us a little bit of a shortcut. Now both these methods work for both flat or curved surfaces. So it doesn't matter what the shape of the surface is like, as long as you can find the weight of the fluid above it and the horizontal force on a vertical wall, you can get the resultant force, the magnitude, and the direction. And we're going to do a demonstration for this process right now. So we have this flood wall. It's around a nuclear power station. We want to prevent flooding at the plant site in case the river floods. There's a circular section at the bottom. So there's a circular section here at the bottom, and the radius is 1 meter. and it's topped by this flat wall. So if the river floods to a height of 8 feet, which is about 2.43 meters, find the net force per unit length on the wall. We don't know the depth of the wall into and out of the page yet. So we're going to use the imaginary vertical plane to calculate the x direction force. So we can say that F in the x direction is equal to the integral of area of pressure the area. So we're going to integrate from 0 to the depth of rho g. The depth is going to be h minus y, and then d area is going to be w dy. So width of the into and out of the page, and dy is the differential height. Now we are interested in solving for force per unit width, so in the end we're going to get force per unit width. And now we have to integrate rho g h minus y dy. And when we do that, we get rho g times h squared minus h squared over 2, which of course is rho g h squared over 2, and this is going to give us a value of 29.1 times 10 to the thirds newtons per meter depth. We can do the same thing with the force in the y direction. We use the weight of the supported fluid plus the atmospheric pressure. So Fy is going to be equal to negative, because the force is going to be pushing downward, atmospheric pressure times the width of the region times its depth into the page. The width here is r, the same as the radius of curvature, plus density times the volume of this region. Now the volume is h minus r times the width into the page. So that's the volume of this section above the curvature part, plus the volume of the curved part, which is going to be pi r squared over 4. So in the end, we can get times the width in the page. So we get Fy over the width is negative hr minus r squared plus pi r squared over 4 times the density plus the atmospheric pressure part. And this becomes negative 123 times 10 to the third newtons per meter depth into the page. So we can use these simplifications to make the math quite a bit easier.